Good day. So our next topic will be influence line. So if we say influence line, this is the graphical representation of the response of a structure subjected to a moving load. So since our focus here is about moving load or live loads, so there will be a variation of the shear or the reaction or a moment of a specific point of a given structure. So we can analyze the reaction or response of a structure using influence line. So let's have an example. So for example, for this beam, so we have a simple support A and which is a hinge, a roller support B. Then we have a point C somewhere between A and B. So let's say required the influence line for the vertical reaction at A, the shear at C, and the moment at C. So how do we start the analysis? I have to construct the influence line of the following. So again, influence line can represent the variation of a reaction, a shear, and a moment of a specific point of a given structure. So first, we may analyze or we may construct our equation using equilibrium. So first, we are to place a 1 unit load that will represent the moving load for various values of x, then do equilibrium equation. So let's say we are placing 1 unit load at a distance x from A. So let us compute for the support reactions. So let's say this is By and let's say this is Ay. So we may do summation moment about A equal to 0, clockwise moments to be positive. So that will be the same as 1 times x minus we have b sub y, this is multiplied by a equal to 0. So we'll be having the vertical reaction equation for y, that is the same as transpose, that is the same as x over 8. So this is the vertical reaction equation for b sub y. But the required is the vertical reaction at A, so we can have it by summation of forces, vertical equal to 0, upward forces to be positive. We have Ay to be upward, plus, what is the value of By? This is x over 8 minus the 1 unit load equal to 0. So we'll be having the equation of the vertical reaction at A, that is Ay is equal to 1 minus x over 8. So this is our equation. So to have more a systematic, let's say, procedure, so let's tabulate. So if we have now the equation, we are to prepare the table. So for any value of x, what will be the value of the vertical reaction at A, that is Ay. So let's say at x is equal to 0, we have what is 1 minus 0 over 8, that is the same as 1. Then we have at x, let's say at x equal to 4. So that is 1 over 4 over 8. That is the same as 1 minus 1 half. That is the same as 0.5. 1 minus 1 half is 1 half, 0.5. Then at x is equal to 8, for example, what is 1 minus 8 over 8? That is the same as 0. Then at x is equal to, on the tip we have the same 12. That is 1 minus 12 over 8. What is 12 over 8? That is the same as 3 over 2. 1 minus 3 over 2 is negative 1 half or negative 0.5. So these are the values for any value of x, the corresponding reaction, vertical reaction at A. So if you are to draw for the influence line for the vertical reaction at A, so let's say this is the influence line for the vertical reaction at A. Let's say at Ay. So what is the value of Ay when x is equal to 0? That is, we have 1. So this is 1. What is the value of the Ay when x is equal to 4? That is, we have, let's say 0.5. At x equal to 8, the value of Ay is 0. At x equal to 12, we have that as negative 0.5. This is negative 0.5. So this is the influence line of the reaction, vertical reaction at A. So we have that equation AY is equal to 1 minus, we have 1 minus x over A. So one advantage if we are using the influence line, we can tell at what value of x, okay, thus the reaction at A is maximum. Obviously, 100%, if the load is over point A or over support A, the vertical reaction at A is the same as 100%. So at that point, okay, AY is maximum. Okay, that is the influence line for the vertical reaction at A. How about the shear at C? So if we are using the equilibrium procedure, so we are to cut this portion, we are to cut point C, cut and expose. So we are to cut that portion at C. So let's say we are to consider this distance first, just before point C. So we will be having a boundary limit, or we have our boundary that is at x equal to 0, less than or equal to 0, less than 4 meters. That will be our limit. So we are placing again the 1 unit load. This is 1. At a distance x, from A. Take note, our limit or our boundary will be up to just before 4 meters. So if you are to cut and expose, the direction of shear at this point is downward, and the moment is counterclockwise. Okay, so first, let us just construct, or let us just establish the equation of the shear at C by equilibrium, summation of forces of vertical. So summation of forces vertical equal to 0, upward forces to be positive. So what is our upward force? We have 1 minus x over A, minus the shear at C, minus the 1 unit load, and this is equal to 0. What will be our equation for the shear at C, considering our boundary from 0 is less than or equal to x, less than 4 meters. So this is the same as 1 minus 1, that is the same as negative x over 8. Okay, so this is our shear equation for C on this boundary. So what if we are to consider that the 1 unit load is already after point C? So we have here the 1 unit load, so we are to remove this one. Okay, from 0 to 4, for example. So we are to use still this section, we are to use this section by summation of forces vertical. That is, we just remove the 1 unit load. We have by summation of forces vertical equal to 0, considering this section. And we have upward forces to be positive. So what is the upward force? That is the vertical reaction at A, 1 minus x over 8, minus the shear at C is now equal to 0. So we'll be having the shear at C is the same as 1 minus x over 8. So what is the limitation of this, or the boundary of this shear equation for C? That is at 4 is less than, or less than x, less than or equal to, okay, that is up to 12 meters. So that will be our boundary equation. So again, after establishing our equation, we are now to tabulate. Okay, so for any value of x, we have the corresponding value of the shear at C. So let's say at x is equal to 0, we have that equation. First, we have the shear is at C is equal to negative x over 8. So that is at 0 over 8, that is the same as 0. So let's say at x is equal to 2 meters, what will be that value? That is negative 2 over 8, that is the same as negative 1/4. That is negative 0.25. At x is equal to 4, we have negative 4 over 8 is negative 1/2 or negative 0. This is negative 0.5. So take note that this equation has a limitation at 0 is less than or equal to x less than 4. So we are considering just before point C. Let's say this is the negative side. So now we are to consider just after point C. What is our equation on that side? We have the shear at C is equal to 1 minus x over 8. Our limit or boundary 4 is less than or less than x, and less than or equal to 12 meters. So we'll be having the portion of 4 on the positive side. Let's say just after point C. So that is the same as 1 minus 4 over 8. That is the same as 1 minus 1/2. That is positive 1/2. Positive 0.5. Okay, the next, let's say at x is equal to 6. What is 1 minus 6 over 8? 1 minus 3/4 or 1 minus 0.75 is 0.25. At x is equal to 8, 1 minus 8 over 8, that is 1 minus 1, we have 0. Okay, at x is equal to 10, what is 1 minus 5 over 4? 1 minus 1.25 is negative 0.25. At x equal to 12, 1 minus 12 over 8, that is 1 minus 3 over 2. That is equal to negative 0.5. So this will be the corresponding equivalent of the shear at C for the various values of x. Now, if you are to draw for the equivalent influence line for the shear at C. So let's say this is influence line for the shear at C. So let's say at x equal to 0, this is the same as 0. We may proceed at x is equal to 4, that is negative 0.5. Okay, this is a negative 0.5. Okay, that is just before point C. What about just after point C? We have positive 0.5. So let's say from negative 0.5 to a positive 0.5. At x is equal to 8, we have 0. And then at x equal to 12, negative 0.5. So this is equal to negative 0.5. So this will be the graphical representation or the influence line for the shear at C. Next, we are to do the influence line for the moment at C. For the influence line for the moment at point C, so let us again cut and expose point C. Then we place the 1 unit load, let's say at a distance x from support A. We have the support reaction at A as 1 minus x over A. Okay, then we are to do summation of moment about point C equal to 0, clockwise moments to be positive for the equilibrium procedure. So what will be the positive moment about this point? We have, let's say this is point C, that is, we have 1 minus x over 8 at a distance of 4 meters minus, this is 1. This distance is the same as 4 minus x. So we have 1 multiplied by 4 minus x, considered to be counterclockwise, moment at C equal to 0. We have the equivalent of the moment at C is equal to, okay, we have this is 4 over 8 is 1/2 of x minus 4 plus x. So we have moment at C is not equal to, I cancel 4, negative 1 half of x plus x is 1 half of x. So this equation is from 0 less than or equal to x less than 4 meters. So what about if we are to assume that point 1 already passed point C? So let's say we are to remove that 1 unit load. So let's say it is already just after point C. Alright, so we are still considering this section, this cut section for the summation of moment about C equal to 0, clockwise moments to be positive. So it's the same as we have 1 minus x over 8 multiplied by 4 meters. Okay, we have now minus the moment at C equal to 0 since we don't have the 1 unit load. It already passed point C. So we'll be having the equivalent of moment at C as 4 minus 1 half of x. So this equation is good for the boundary. We have 4 is less than x less than or equal to up to 12 meters. So let us tabulate. So for any value of x, what will be the value of the moment at C? So first, using the equation, we have the moment at C is equal to 1 half of x. So the limitation is from 0 up to 4. So let's say at x equals 0, so 1 half times 0 is 0. Let's say at 4, let's say this is the negative side supposedly, just before, let's say just before point C. That is equal to, what is 1 half of 4? Obviously, there is 2. Okay, the next, we have the other equation, that is, the moment at C is equal to 4 minus 1 half of x. So for example, we are using again 4 meters on the positive side. That is just after point C. That is 4 minus 1 half of 4. That's the same as 4 minus 2. So as you can see, we'll be having the same value of 2. Okay? Then let's say we have 8. What is 4 minus 1 half of 8? We'll be having a value of 0. Let's say at x equal to 12. What is 4 minus 1 half of 12? That is 4 minus 6. We have negative 2. So these are the ordinates for the influence line for the moment at C. So let's say this is the influence line for the moment at C. So let us just plot the values. At x equal to 0, that is the same as 0. At x equal to 4, that will be positive 2. This is positive 2. At x is equal to 8, we have 0. At x is equal to, at x equal to 12, that will be negative 2. So this will be the influence line for the moment at C. So where do we have, where can we find, or where do we put the 1 unit load to have a maximum moment at C? That is, at point C itself, we can have a maximum positive. As you can see, this is a positive 2. So if we have a 1 unit load, for example, if we have the load just over point C, we'll be having a maximum moment about point C, the maximum positive moment. What about if we place the load, let's say on the free end, that is at x equal to 12 meters, if the 1 unit load is on this point, the corresponding influence line ordinate is negative 2, we'll be having the maximum negative moment about point C if we are to place a load on this point. So this is our introduction for the basic concept of influence line.